Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we're talking about standing waves, of course, on a string, let's say, or some other musical instruments. And of course, previously we did talk about standing waves. We said standing waves will happen when two waves, let's say, pass, let's say in opposite direction, let's say, or of course in opposite direction in a given medium. But for these two waves to create or to form a standing wave, they must have the same frequency, wavelength, and of course amplitude as well. Then of course they will form a standing wave there. And of course you do know that standing wave is the result of constructive and destructive interference. Where in the standing waves, of course, we will get nods and antinods, yeah? And of course you do know what are nods and antinods. In the previous lesson we did talk about the fundamental frequency, yeah? And of course, let's say when a string is struck, a standing wave will form on that string. And of course, let's say, and in order for the standing wave to form, there must be, let's say, on a string, by the way, the two ends of the string must be nods, and of course, we will have some antinods as well. At least, let's say, one when the string is vibrating with a minimum frequency. The minimum frequency of vibration for standing wave, we did call that one fundamental frequency, yes? And of course, when the frequency is the lowest, then of course, what is maximum in this case? The wavelength will be the maximum. Considering the speed of, let's say, the speed of the, let's say, the speed of sound in this case is the same, okay? So we have, of course, we did talk about fundamental frequency, let's say. So fundamental frequency is the lowest frequency of a vibrating of a standing wave, let's say. And of course, we said if a string vibrates with two nods and one antinod, of course, then the wavelength that is produced will be maximum in length, let's say, and of course it will be minimum in terms of frequency. All right, we do know that speed of, let's say, speed of the sound is basically V equals to what? Equals to lambda times the frequency. If we're trying to find the frequency of that, let's say, maximum wavelength, then of course, then we'll, frequency equals to speed of the wave, let's say, divided by the wavelength. But we said the wavelength equals to 2 times the length, so this is the final equation. So F1, that is called fundamental frequency, equals to speed of the sound, let's say, divided by 2 times the length of the string. And of course, we did solve this example. Then after that, we talked about harmonics. We said, what are harmonics? Harmonics are a series of frequencies that includes the fundamental frequency, and of course, also integral multiples of the fundamental frequency. So of course, we have fundamental frequency and then multiple of that, or let's say integral multiples of that frequency. Let's say if fundamental frequency is, let's say, 1, of course, we can say integral multiples of that frequency, it could be 2 times that, yeah, 3 times that, or 4 times that. These are basically, we can say, harmonic series. And then after that, of course, we covered harmonics. We said it is an integral multiple of the fundamental frequency. So of course, we said fundamental frequency equals to what? Fundamental frequency equals to, we can say, we did say this, yeah, equal to V, of course, divided by 2 times the length. But when we talk about harmonic series or harmonics, of course, we have something like this. Fn equals to what? N times what? N times the fundamental frequency here. This N, of course, for a string, don't forget, it could be 1, 2, 3, 4. These are, you can see that these are integral multiples of that. So of course we have even, we have odd numbers and even numbers, or you can say all the even and odd numbers that we have, of course. So these are basically, you can say what? You can say harmonics, of course. N would be the number of harmonics. By the way, so these are basically when a string is cut, yeah? So depending on, let's say, depending on the length of the string, let's say, or the length of the wavelength, let's say, and of course we can have different harmonics or different frequencies, yeah? These different frequencies, we can call them what? We can call them harmonics. All right, so and of course, you can say, by the way, when we have, let's say, the fundamental frequency, when a string is vibrating, let's say, with a minimum frequency of a standing wave, let's say, in that case, we would have 2 nods and 1 antinod. And of course, we said to find the wavelength, we can always use this equation. Wavelength for the fundamental, that would be 1, yes? Okay, equals to 2 times the length divided by what? Since it is we said divide by n. Or, by the way, this n here on a string is equal to the number of antinodes as well. So since it is the first harmonic, so we'll say 2 times the length divide by 1. Or if I ask another question, how many antinodes do we have? That is also 1, yeah? What about the second, let's say, harmonics, yeah? So for the second harmonic, that is going to be wavelength of the second harmonic equals to 2 times the length divided by n. Remember, we said n is the number of harmonics. Second harmonic, that is 2. We said n is also equal to the number of antinodes. So take a look at the second harmonic. How many antinodes do we have for string? That is also 2. All right, so of course you can go ahead with third harmonic and fourth harmonic and of course so forth. And then we said we can have an equation for that, yeah? We can say a general equation for standing wave on a string or vibrating string, of course. We say Fn equals to what? Fn equals to, not this, right? Fn, all right, equals to n times v over 2l. Don't forget, this n once again represents the number of harmonics, by the way, yeah? Number of harmonics. And of course, these are, you can say, the fundamental, or you can say the frequency, yeah? All right, so we can say, of course, the first harmonic, second harmonic, third harmonic, these would be the frequencies of these harmonics. So for example, if they ever ask you to find the frequency of the first harmonic, we'll say F1, right? So first harmonic, that is going to be 1 multiplied by what? Because this n is 1, speed divided by 2 times the length here. What if it is the second harmonic, right? We can say frequency of the second harmonic, that is going to be 2 times speed divided by 2l. And of course, it goes on and on. That is for a string, don't forget. All right, so now this question here, question 22, that is where we stopped last time. It says, what is the fundamental frequency and how are harmonics related to the fundamental frequency? Now, do you remember the definition of fundamental frequency? We said fundamental frequency, or F1, it is the lowest frequency of a vibrating, let's say, or vibration of a standing wave, yeah? That is, let's say, for a string, you can say. All right, and then harmonic would be the integral multiple of that fundamental frequency. So once again, fundamental frequency, that is the lowest frequency. Harmonic would be the integral multiples of that fundamental frequency, like 1 times that frequency, 2 times that frequency, 3 times that frequency, and so forth. Okay, so now we have a question that says, one of the following is correct to find the harmonic series of a standing wave on a vibrating string. Remember this, whenever you have a string, we have an equation for that, yeah? It says what? To find the harmonic series, don't forget. Whenever it says harmonic series, that means all the harmonic series can be included, yeah? And of course that is 1, and then the second key is for a vibrating string here, okay? Because later on you will see that we have pipes that are open at both ends or could be open at one end here. So it is very important to know or recognize that is a vibrating string here. So what was the equation that we had for, let's say, the series of harmonics? And of course that was what? That was Fn equals to n times v over 2 times the length. You will see that this would be for, let's say, a pipe that is open at one end. Later on you will see that. And of course these are different because these are, you know, like the inverse or the revert of, let's say, v should be, or the speed should be up the fraction, and then 2l should be below. And of course this one is also incorrect. So the correct one is going to be option A here. Take a look at this one here. It says, which of the, or which of these is the harmonic series of a standing wave on a string? So now we're talking about harmonic series here, all right? So we said number of harmonic or harmonic series, that would be the integral multiples, yeah? So what are the integral multiples? We said, if you remember, we said we have both even and odd numbers here, yeah? So which one of these one, later on you'll see that these are, that is going to be for a pipe that is open at one end here. This is incorrect because these are just even numbers, yeah? These are, you can see here, there is irregular pattern here. And about this one here, you can see we have odd and even numbers. Of course, this is the correct one for the series or number of series of standing waves, let's say. All right, now take a look at this one here. It says, the figures below show a stretched string vibrating in several of its modes here, okay? if the length of the string is 2 meters, so what is the length? 2 meters. What is the wavelength of the wave on the string in A, in B, in C, and in D as well? All right, now let's solve this one here. And how do we approach solving this? First of all, we know that it is a string, yeah? So what is the equation that we use for a string? We said f, right? By the way, there are two equations we can use, yeah? We can say fn here equals to what? Equals to n times f1, yeah? That is 1. But here's a question. Do we have f1? No, right? So let's just ignore this for a second here. We will use the other equation since we are given length, yeah? If we're given length, by the way, we're given, so we're given length, yeah? It says find the wavelength here, true? So we do know that wavelength equals to what? Wavelength equals to 2 times the length that is for this one here. But since we have numbers of harmonics, you can say, so in this case, of course, we will use the other equation that we had. And what was the other equation? Of course, we said we can say L, right? We can say lambda n equals to what? Equals to 2 times L over n, yeah? Remember, what is this n standing for? It stands for the number of harmonics in this case. So we have, in this case, now this is going to be the first harmonic, yeah? How do we know the first harmonic? There are two ways you can say this, yeah? You can see the vibration here, the wavelength is the maximum, that is 1, or you can say we only have one antinode, yeah? So do you remember this? We said wavelength here, you can say the first one equal to 2 times the length divided by number of nodes, but this number of nodes is the same as the number of antinodes here. Sorry, my bad. This number of harmonics, not node, equal to is the same as the number of antinodes here. So we'll say 2 times the length. What is the length here? The length is 2 meters. So divided by how many antinodes do we have? That is 1. So 2 times 2, that is going to be 4 meters. That is the first one, yeah? What about the second one here? Second one, of course, we can say, once again, 2 times the length, right? Since it is the second one, take a look. How many number of, let's say, antinodes do we have? That is 2. Or you can say second harmonic, yeah? And of course, it's going to be 2 times 2 divided by 2, of course. Now that is 4 divided by 2. These two cancel out. Of course, we have 2 meters. What about the third one? Yes? In C, we have 3 antinodes. Yes? So of course, use the same equation. Let me do it at the other side. So we can say the wavelength, again, 2 times the length divided by 3, because we have 3 antinodes here. So 2 times 2, that is 4 divided by 3. That is going to be 1.33. Yeah? That is in meter. What about the last one, D? Right, you can see here 1, 2, 3, 4. So we can say the fourth one here equals to 2 times the length divided by the number of antinodes, so divide by 4. So 2 multiplied by 2, or 2 times 2 divided by 4, that is basically 4 over 4, which is equal to 1 meter. Very good. So these are basically the wavelength that we have. What if I ask you find the frequency here? Would you be able to do that? Yes, if the speed is given, yeah? So if the speed is given, right, knowing the frequency of, or the first harmonic, then of course you can find the second, third, and fourth harmonic very easily. All you have to do just, if this is the first harmonic, you can say 2 times the first harmonic, or 3 times the first harmonic, 4 times the first harmonic, and so forth. You will see that we're going to get into some questions that they are asking us to do something like that. All right, take a look at this one. What does it say? It says, what are the first 3 harmonics? By the way, it's very important to know this. When it says find the first 3 harmonics, that means you have to find what? Find F1, right? F2 and F3 as well. Why? Because we want the 3 first, or the first 3 harmonics. So on a string, don't forget, the first 3 harmonic is going to be F1, F2, F3. Later on, you will see that the first 3 harmonics, if it is for a pipe that is open at one end, will be different. But for strings, which we're dealing with so far, the first 3 harmonics is going to be first, second, and third. All right, for a node that is produced on a 31.0 centimeter long violin string, if the waves on this string have a speed of what? A speed of 274.4 meter. All right, so let's do this first. All right, we can do this in 2 different ways. But first of all, you still have or need to find the first, let's say, harmonics. Yeah. So the first harmonic, remember this. Right, right, we'll say F1, right, equals to what? What is the equation? Or let's write the general equation first. Fn equals to n times v over 2L here. So we won the first harmonic, so of course it's going to be 1 times v over 2L, yes? So 1 times v over 2L, that is still v over 2L, yeah? But let's do it again, yeah? So keep doing this. So 1 times, what is the speed of the string, let's say, or yes. So that is 274.4, right, divided by 2L, 2 times. But remember this is in centimeter. You have to convert to meter, so it's going to be 0.31 meter. So 0.3 meter. And of course, the answer is going to be what? The answer is going to be 443 hertz, yeah? Use your calculator and make sure that it is the same number as well. Now, after this, right, we can find the other two harmonics very easily. And how do we do that? Remember this. We can use the equation that I've used before. So we can say Fn equals to n times what? F1, right? F1. So we want the second harmonic. So we'll say F2 equals to what? 2 times F1. So in this case, it becomes 2 times, what is F1? That is 443. So the answer is going to be what? Going to be 886, yeah? That is this one. Yeah? What about the third harmonic? We'll say F3 equals to 3 times F1, yeah? So 3 times 443, and that is, of course, 1,329 hertz. If I don't use this, what else can I use, yeah? Remember, I can use the equation for all of them as well. Let's say the second harmonics is going to be n times 2L over, my bad, it is going to be speed over 2L, yeah? So in this case, second harmonic is going to be 2 times that speed, that is basically, it is given, which is 274.4 divided by 2 times 0.31, yeah? All right, very good. Then, of course, you will get the same result, which is going to be 886, that is in hertz, yeah? Because these are frequencies. You can write hertz as well here, right? Because these are frequencies. Okay, for the third harmonic, you can do the same thing, but instead of this n, instead of using 2, of course, you need to use 3n in this case. But as long as you find the first harmonic, the rest is going to be very easy, and that is all you need to do. All right, take a look here. It says, what is the third harmonics of a note on a 31 centimeter long string if the wave on the string have a speed of this much? That is exactly the same as this question. But remember this, we don't have, right, they don't ask you to find the first and third, let's say second harmonics. But in order to find the third harmonic, you still, as a matter of fact, you don't need the first harmonic. You can just go ahead and use one equation and then you can find the answer, yeah? So third harmonics is going to be F3, which is going to be n times what? N times v, right? That is the speed over 2 times the length, yeah? So since it is third harmonic, that is 3 times speed, right? It is given 2 times the length is given, but you have to convert into meter, and then of course you can find the third harmonic, and of course that is going to be in hertz. Very easy. All right, take a look at the next one. It says, a standing wave is produced on a vibrating string fixed to both ends. So remember, it is still a string here. It says, if the frequency of the third harmonic of the string is this much, and the speed of the wave on the string is basically 345 meters per second, what is the wavelength of the longest wave? We don't want the frequency, by the way. What is the longest wave produced on the string? Now, this is very interesting, and let's do this, yeah? All right, so let's get a rectangle. All right. Let's get a bucket. All right, turn this one to white. All right, watch this. Let's move this one a little bit up as well. All right, take a look. What does it say? We have a stamp produced on a fixed, let's say, string that is fixed to both ends. That's one. If the frequency of the third harmonic, yeah, on the string is this. So, of course, F3, you can say it is equal to what? Equal to 575 hertz. all right? And the speed of the string, you can say, or on the string equals to what? Equals to 345 meters per second. So find what? Find the longest wavelength. So what is the longest wavelength produced? Remember, the longest wavelength produced equals to what? Equals to 2 times the length, yeah? Remember this. That is, of course, the minimum vibration, but the maximum wavelength you can see. But what you see here, I have the third harmonic, yeah? So in another word, what I need to find is I need to find the length of the string, yeah? So how can I find the length of the string if I have the third harmonics, yeah? So write the equation for the third harmonic. In this case, we'll say F3 equals to what? Equals to M times V over 2L, yeah? Since it is the third harmonics, so that means 3 times V, okay, so let's plug in the numbers here, right? Let's plug in the numbers directly. So what is the third all right, I think not this. So what is the third harmonic here in this case? The frequency that is given is basically 575 hertz, yeah? Remember, since it is the third harmonic, so this n is going to be 3 times. What is the speed of the speed of on the string, let's say, yeah? That is basically, it is 345, yeah? And then, of course, 2 times the length. L is not given, yeah? So I can, of course, swap these two. I can say L equals to 3 times 300 what? 345, and then, of course, divided by 2 times 575, all right? Let's double check with the numbers. Third harmonic, that is 3, speed of, let's say, on the string, that is basically 345, that is also correct. And then the frequency is 575, that is also correct. So now do the calculation, you will find what? You will find the length. What is the length? You can use a calculator, or let me see what is the answer there. So we have 3 times what? 345, right? And then divided by 2 times 575. Oops, what is this? 575. So the answer is going to be 0.9, yeah? The answer is going to be 0.9, but 0.9 what? 0.9 meter, of course. So length equal to 0.9 meter. But remember, that is just the length of the string here. The question says, find the longest what? The longest wave produced. So of course the longest wave produced when we have, let's say, or when the string is like this, here's the vibration of the standing wave, yeah? So we found the length, which is 0.9, but remember, the wavelength for, let's say, or the maximum wavelength, it equals to what? Equals to 2 times the length. So 2 times 0.9 meter, and of course that is 1.8 meter. So which one of the option is this? That is option C in this case. Okay, so this is how it is done. Remember this, you might just find the length and you might say, oh yes, this is basically, or whatever, yeah, this is the longest wavelength. But no, remember, the longest wavelength equals to 2 times that length of the string, and of course equals to 1.8 meter. All right, moving to the next one. Standing waves in an air column, yeah? So remember this, we have standing waves, of course, on a string, yeah? Now we're talking about standing waves, let's say on a pipe, yeah? That is open at both ends here. You will be, soon you will notice that in terms of the harmonics, in terms of the wavelength, these are all the same, but there is one difference which I'm going to tell you in a moment. So it says, standing waves can be set in a tube of air, yeah? So for example, like these musical instruments, it could be for something like, for example, a flute or any other musical instrument. It could be a saxophone, let's say. Standing waves can be set up in a tube of air such that inside a trumpet, column of a saxophone, let's say as well, yeah? So while some waves travel down the tube, so as you can see here, some waves travel down the tube, of course, and then these waves that are moving down the tube will be reflected. So of course, now these waves have the same frequency, wavelength, and amplitude, and they are moving in opposite directions. So what will happen? Standing waves will be formed, yeah? Very good. So the waves traveling in opposite direction combine to produce what? To produce standing waves. So many brass instruments and wood winds produce sounds by means of these vibration or vibrating air coulombs. So watch this. Now we have basically, right, let's say coulombs of air, or let's say pipes, all right, you can say for short, okay? These pipes, or some of them, all right, you can see that both ends are open, and some others you can see one end is open. So this is a huge difference for what we're covering, so I want you to notice this. So if both ends of a pipe are open, then all harmonics are present. Do you remember what were harmonics? So previously we said harmonics is basically, let's say we said F equals to what? Fn. Let's use blue, all right? So we said, I think I'll have to press this. All right, it is on the other side. All right, so we can say F. Oh, I think I'll have to get it back on the other side. Okay. So now what we have is this. Let me zoom out this for a second. So in the previous, when we had a string, of course, we said number of harmonics, or when we're talking about harmonics, of course, we said Fn equals to n times what? Times the fundamental frequency, yeah? So let's go back one more, right? So n times what? N times F1. We said if for a string, of course, n can equal to 1, 2, 3, 4, and of course so forth, yeah? So odd and even numbers, yeah? These are all harmonics, you can say, yeah? So this is what we said. That was for these, for string, yeah? We do have the same thing for a pipe that is open at both ends. We say all harmonics are present. What does it mean? That means we can apply or use the same equation. We can say Fn equals to n times F1, fundamental frequency. So once again, n here equals to what? That is harmonic number, yeah? It can equal to 1, 2, 3, 4, and so forth, of course, yeah? So you can see all harmonics can be present if we have a pipe that is open at both ends. So how does it form? You can see here. But, so what is the difference between an open that is, or a pipe that is open at both ends, or a string here? Now, let me tell you this as well. So for a string, we had this, yeah? For a string, or when we dealt with string here, we said the ends of a string are basically become what? Become knots here, yeah? And of course, these are knots, and of course, we had, let's say, an anti-knot here, all right? An anti-knot. Right? So you can say 2 knots, 1 anti-knot. And of course we said the length equals to half, right? The length equals to what? The length equals to half a wavelength, or you can say wavelength for the fundamental, you can say wavelength here is going to be, or maximum wavelength here equals to 2 times the length here. And of course for the frequency we said equals to speed, let's say on the string equals to what? Equals to 2 times the length here. That is fundamental frequency as well. But what you see here, if it is for a pipe that is open at both ends here. So here's a pipe. When do we have a standing wave? Remember this. Let's say here is a wave that goes down, let's say, and of course this wave is reflected. So you can see here, this is not a good drawing here. So let me redraw this. Right? Let's choose a different color. Right? So you can see the difference here. All right, so what you see here, if it is for a pipe that is open at both ends, what do you see so far? You would see that the ends of the pipe are anti-knots basically, right? And of course we have 1 knot in here, you can see, yeah? So you can say something opposite to this. Here on a string, the 2 ends are knot, and of course we have 1 anti-knot. But what you see, let's say that is a pipe, right? Pipe that is open. Open what? Open at both ends, you can say. At both ends, right? And of course you can see a string here. When we say string, of course, you can see the string is attached at both ends, or fixed to both ends, you can say. All right, so this is the main difference between, you can say, if it is a string, in terms of harmonics, harmonic series and all that, you can say, or in terms of amplitude and all that. By the way, here, you can see that basically the distance between, what we have is the distance between one anti-knot to another anti-knot that is also half a wavelength, by the way. So we can say the wavelength, or if this is the length, right, of the pipe in here, we can say the length of the pipe equals to half a wavelength, or a wavelength here equals to 2 times the length of the pipe in here. you can say this is the fundamental wavelength here, yeah? By the way, the fundamental wavelength is going to be the maximum wavelength, by the way, yes? And if the wavelength is maximum, what about the frequency? The frequency will be minimum in this case. So we can say f1 equals to what? Using that equation, speed equals to the wavelength, but the wavelength equals to 2 times the length, and this is basically the fundamental frequency. And then for harmonic series, we can say that is for, once again, for a pipe that is open at both ends, f1 equals to n times the fundamental frequency. Once again, this n can be 1, 2, 3, 4, and of course, so on, yeah? So this would be, or you can say the number of nods and antinod here and there would be the major difference between the two. Otherwise, in terms of the wavelength, the fundamental frequency, the harmonic series, these are all the same between the two here. All right, so as you can see here, first harmonic, second harmonic, and third harmonic, and so forth, as you can see here. So what is the main equation that we can use? We can say harmonic series for a pipe that is open at both ends here equals to what? Fn equals to n times speed, let's say, and of course speed of course divided by 2 length, where n, the number of harmonics, equal to 1, 2, 3, and so forth. And of course you can see that is the speed of sound in the pipe. You can say measured in meter per second. Fn, that is the frequency of the nth harmonic, and then n is the number of harmonics, while L is the length of the vibrating pipe. Because we said it is the same for string as well, so we can use the same equation. If that is for string, we can say L is the length of the string, which is also measured, which is always measured in meters. These are some of the instruments, of course, that you can say we have instruments, let's say, with, that are open at both ends. You can say, by the way, sometimes the question, if it is not very obvious that, like, the instrument that is given, whether if it is one end open or both ends open, the question will always clarify. For example, when they tell you clarinet, sometimes, let's say, they might tell you one end is open or 2 ends is open. Yeah, it depends on. So you don't have to worry about the names of these or like how many sides or how many ends are open, because the question will always tell you. But remember this, if it is 2 ends open, here's the equation that you will need to use. All right, take a look here. It says we have a study tip here, which is a bit different than previous ones here. It says increasing the temperature will increase the speed of the sound in the air, which increases the frequency of the sound. That is a bit different when it comes to standing waves and of course when we're talking about harmonics. Because if we go back to this, or what was the equation of harmonics here? We said fundamental frequency equals to what? Equals to n times v, that is basically the speed of sound in air, yeah? Divided by what? Divided by 2 times the length of the windpipe, let's say, or the instrument, whatever the musical instrument is. Or it could be the length of the string if we're using a string here. But for this, okay, when we're talking about sound or speed of sound in the air, you can see here, all right, assuming that the length of this musical instrument doesn't change, by increasing the speed, what do you think will happen to the fundamental frequency? Because these two are directly proportional, so increasing the speed here will increase the fundamental frequency slightly. For a normal person or an ordinary person, we might not feel the difference, but if for a musician, when the temperature changes, let's say for sort of like by 5 degrees or so, let's say they can feel the difference. They can feel the difference in notes that are produced by musical instruments, because of course the temperature affects the speed. Yeah, the higher the temperature of the air, of course, let's say the faster the speed of sound in air, yeah? That, of course, will change the fundamental frequency. But once again, it is not that much that you and I can hear. But if it is a musician, of course, they might be able to hear the difference. So now, of course, why are we studying this? Or I'm telling you this because I have a question related to this. Right? And the question is also telling you this. It says the fundamental frequency of any note produced by a flute here, right, will vary slightly with temperature change. So it tells you that it changes slightly with the temperature change in the air. But it says for any given note, will an increase in temperature produce a slightly higher fundamental frequency or slightly lower fundamental frequency? So the question tells you that the temperature will affect the fundamental frequency. Yeah? It will change it. But the question is, will it increase the fundamental frequency or it will decrease the fundamental frequency? And how do we answer this question correctly? You'll have to write the equation of the fundamental frequency. What is the equation again? We do know that the equation of the fundamental frequency equals to what? Equals to, we can say, fundamental frequency, let's say, equals to what? Equals to, let's say, n times, let's say, v over 2L, yeah? Or speed over 2L. Fundamental frequency, that is 1, so 1 times v over 2L, yeah? So now that is the length is fixed here, let's say. So you can see what is the relationship between speed and fundamental frequency. These two are directly proportional. So by increasing the speed, the fundamental frequency will increase. All right, remember, because the relation between fundamental frequency and speed, these are directly proportional. So increasing the speed will increase the fundamental frequency. But of course, this change is very small, you can say. So of course, to answer this, we'll say increasing the fundamental frequency. Let's zoom in a little bit. Increasing the temperature, right? Increasing the temperature will increase the speed of the sound in the air, which increases the fundamental frequency of the sound. Remember, V is directly proportional to the fundamental frequency, or vice versa. You can say fundamental frequency is directly proportional to V, of course, when L, or the wavelength, is constant, you can say. All right, now take a look at this. Now, so far, we've learned about citrings and, of course, pipes that are open at both ends. Yeah? And, of course, we said in terms of fundamental frequency, there's no difference. Yeah? In terms of harmonics or number harmonics, there's no difference as well. Okay? So let's answer these questions so far. It says, in a pipe that is open at both ends. Yeah? Why are we saying at both ends? Because later on you will see that we'll have a pipe that is open at one end only. So it is very important to notice this, which it says open at both ends. Yeah? Because if it open at both ends, of course, then the fundamental frequency or harmonic series equal to n times v over 2L. Yeah? And of course, we said this n equals to 1, 2, 3, all the harmonics. You can say will be available. So in a pipe that is open at both ends, it says only even harmonics will be available. So in order not to cause confusion here, let me write all this properly. So 1, 2, 3, 4, and even 5, and goes on, yeah? So the first option says only even harmonics are present. Only even harmonics. It says only even harmonics, like 2, 4, 6, 8, these are present. Is this correct? No, because we have let's say odd and even ones, yeah? So not A. What about B? Only odd harmonics are present. Only odd harmonics, that means 1, 3, 5, 7, 9, and it goes on, yeah? So this is also incorrect. C says both of even and odd harmonics are present, and of course that is the correct one here. Yes? What about D? Says no harmonics are present. That is incorrect. So the correct answer is going to be C here. Take a look at the second question. It says, one of the following is correct to find the harmonic series of a standing wave of a pipe open at both ends. And of course, we went through the equation. Which one is correct here? We said Fn, right, equals to n times V over what? V over 2L. That is the same thing for a string, by the way. So string, right, vibrating string, and let's say standing wave on a vibrating string, and of course, standing wave on an open air column that is open at both ends would have the same equation in terms of harmonic series, by the way. All right. Next says what? A pipe that is open at both ends has a fundamental frequency of 320 hertz, yeah? When the speed of sound in air is 331 meters per second, what is the length of this pipe? All right, good enough. So how about we get this one back? All right. And then let's solve this question and see how it is done, yeah? So make sure you know the information that is given. Okay, so what are we given here? It says we have the fundamental frequency. So that means we have F1, which is basically equals to what? Equals to 320 hertz, right? And we're also given the speed of sound, let's say in air, that is 331 meter per second. Very good. Now, what is the question here? Says part A says, what is the wavelength of this? What is what? What is the length, not the wavelength? So find L here. So how do we find L here? Right, let's change the color to blue. All right, so in order to find the length here, we have fundamental and speed, so you can easily find the length. Okay, so let's say write the equation here. So we can say fundamental frequency, right, or F1 equals to what? Equals to V over 2L, yes? Since it is the first one, you can write 1 here, but 1 times this changes nothing. So can I swap L and frequency because we want to find the length, yeah? So length equals to speed, all right, divide by 2 times the fundamental frequency here. So speed is 331 meter per second, 2 times 330, yeah? So of course, what is the answer now? That is 660, 331, yeah? So let's get a calculator and see what is the length of the string here. 331 divided by 660. That is about 0.5, so we can say the length is 0.5 meter. That is the length of what? The length of this pipe. That is the same thing if it was a string as well, by the way. So 0.5 meter. Okay. All right, what is next? It says, what are the next 2 harmonics? All right, the next 2 harmonics. Now, in order to find this, there is one very easy way, yeah? We do know that Fn equals to n times the fundamental frequency, yeah? So if this is the fundamental frequency, the next one we can say F2, yeah? So F2 equals to 2 times F1, correct? So 2 times, what is F1, by the way? That is 320, yeah? So 2 times 320, it is going to be what? It's going to be 640, right? It's going to be 640, that is going to be in hertz, yeah? What about the third harmonic? Can we just say 3 times the fundamental frequency? Yes, which in this case, 3 times 320, and of course that is what? 0.99, okay? That is, of course, is going to be in hertz as well. So this is how it is done. So 640, 990, yeah? Oh, my bad. This is 320, not 330. So let's erase this. I felt like something was wrong. All right, so 3 times 320. So in this case, is going to be 960 hertz, yeah? By 0, that is going to be 6 and 9. All right, so these are the answers there, of course. 640, 046, that is correct. And of course, that is 069, yes. All right, so these are the correct answers there. You could just see there, yeah? So the length was about 0.5 meter, right? And of course, the second harmonic, 2 times the first or fundamental, that is 640. Third one, it is going to be what? 3 times what? 3 times the fundamental frequency. And of course, here's what you see. All right, so I think that is all for now. Next session, we'll continue from question 34, yeah? Make sure you go through these 2 one more time, right? Because these 2 are very, very important. Of course, if you're willing to solve all these questions or questions that are related to harmonics very easily, make sure you re-watch this video and master all the concepts. Till then, keep practicing, and I'll see you next time. Assalamu alaikum wa rahmatullahi wa barakatuh.